Thank you. So my name is Michael Loweth and I work here at Oxford Space Systems in the business development team. So that means that my role is to be forward facing outside of the company to look at what opportunities exist, to find those people, to talk to them, to explain what we do and how we do it, and then to build those relationships so that we can then work with companies around the world to develop our products and meet their problems and eventually launch things into space. It means that I need to communicate and I need to have a good understanding of my knowledge and of my products to be able to understand where those niches lie, and I need to work with my two colleagues, Shafali and Mike Lawton, to really understand what are the things that we want to be chasing, where do we go with this technology. So I don't know how much you guys know about Oxford Space Systems, but we started in 2013 and got our real seed funding in 2014. 3 guys, I knew them all, good friends, and they started with some really good ideas and they've grown the company at a phenomenal rate. Since then, from 3 people, it's nearly doubled in size every year. So now we are 46 people, and more or less. And the whole focus of this growth has been because the things that we are bringing to market, the ideas that we're developing, are really of interest to both our market in space and to so many others around, because they're quite innovative. And it's things like this. So everyone knows carbon fibre, you make racing cars out of it, it's that solid stuff, isn't it, you know? But what we do is we've looked at the makeup and how we produce this, and we've worked out how we can deploy carbon fibre. So I'll do it in that direction there. So like that. So you can see how we can deploy out what is a very, very light structure. I mean, this version is not so torsionally stiff, but we can develop versions that are. But in particular in this version, it's very strong in compression. So we can push something out, pull something in, and use this as an actuator or to support lighter components when you really need to. We've managed to get this on orbit. I don't know if you can see the picture in the background, but there's a picture that we got from orbit in November 2016, and that was getting this in orbit, showing that it works. And what was really unique about that was on this small, what they call a CubeSat satellite, we made the longest deployable, in fact retractable structure in space. And what is really unusual for space is we got it from concept to deployment in just 30 months. Now, depending on what industry you work in, 30 months can seem quite a long time. But when you're talking about the space industry, you can't go and fix it if it doesn't work. And that makes the space industry inherently conservative. So though we are cutting edge in a lot of our developments, we're also very conservative, and it's almost Jekyll and Hyde, that we want to make sure it works, especially if it's a critical item. Something like the battery. If the battery dies, your satellite dies. Your deployable structure, if it doesn't deploy out your solar rays, you don't have any power, you can't work anymore. So they're critical items, and therefore people don't want to launch something into space if they don't know it's going to work. because of that, the average development time to get something into space, you're talking about 5 years if you're lucky, probably 10 years. And so 30 months is a revolutionary change in pace. And it's a great example of what the space industry is calling new space. So like many organisations, like many industries, computer science for example, space is having its own revolution at the moment, where the traditional people who've worked really hard and will spend 5-10 years developing this before they launch into space, we're now getting this revolution that we're actually realising, well, we've done that for 40-50 years. We know how to get into space. Let's start to accept a bit more risk. And it doesn't mean we want to just throw things up and litter space, and you know, we all have hopefully heard that there's issues where there is lots of space debris up there, but we can work around that, and we can design things that accept a bit more risk and can work at a faster pace, and that allows us to really start to be a lot more radical in what we do in space, and to really bring some new ideas. And that's where people are looking at bringing terrestrial capabilities like broadband internet anywhere in the world. You don't just have to plug in or be at home. You can get that anywhere, and so these kind of capabilities are really revolutionising how we think about connectivity, for example. And that's why I'm in the space industry. It's that kind of real exciting, developing new opportunities, and they're not just about making money. A lot of them are an opportunity to really improve our quality of living, improve our understanding of this earth where we live. You know, I don't want to live in a dump. I don't want to live somewhere where you have to step around rubbish all the time, or wear a face mask because the air pollution is so bad. I want to live in a nice planet. And a lot of space is actually about that. It's about looking after our earth. So looking at where the carbon monoxide, carbon dioxide is being produced, where all these greenhouse gases are. There's then things like GPS, helping us get around. There's the telecoms, the most commercial side, but we use that day in, day out. Every day we rely on space for everything we do, least of all our communications. So that's an important part of what we do here. And Oxford Space Systems is really lucky that can tie into a lot of that, because if I show you here, this is a helical antenna, a great example of trying to get some of that data around Earth. But we want to pack this into a small CubeSat satellite. Now, a CubeSat satellite is something that's 10 centimetres by 10 centimetres by 10 centimetres, and that's 1U. We sometimes need bigger satellites, so you'll have a 2U or 3U, where you put two of these squares together, two of these cubes together, or 3 or 6, or build them up like Lego. But 10U is not very big. It's you've got to really squeeze your engineering to fit that space. And this example of that, so you've got your helical antenna you want, but what we can do here is compress that down so we can fit that into half a U, so half of that space, which then means you've got space underneath it to start to put power, to put your electronics, to do everything else. And then you can deploy this out once you're in space and start to listen out for these signals, so you can start to get information on how your car, how your appliances at home, how different systems are working, and they can just slowly report back to say, hey, I'm getting low on milk, or hey, my tyres are getting low on their tread. We need to start booking this guy in for his garage appointment. And you can start to have machines communicating that low level information so that you're not going to be late for your MOT or something. And that kind of technology we can then scale up. So if I lead over here, I'm not going to deploy this one because this goes 3.5 meters out, but you can see the size of this again compresses very low, very small area, but we can send that right out to give you that nice big long antenna to give you the performance you need for that data throughput. And what we're really able to do is to use our understanding of these basic material technologies, build it up using small examples of this is a structure here, this is a material, this is how this works, and slowly get more and more complex, get larger and larger. And by proving something on space like this, you can do that on a very inexpensive satellite. You can then make a much larger version on a much more expensive satellite, and that risk of failure is reduced because you know it works at one level. You can still be quite risky at how quickly you get that out there, but it starts to de-risk, and this is what new space is about. It's understanding the risk that you're willing to accept, knowing you can't just go and fix it. You can't just go and tweak that bit to improve that bit of performance, but what we can do is show that it works, get it up there, get it operating, see how we can best use that technology, and then improve it from there. We're not trying to design a Formula 1 car now. We start with your mini, your micro, and build up to your racing car, and that's very much, if I don't know how well that'll come up, but at the entrance we got one of these large helical antennas, and we recently got a press release out where we've been awarded some money from the UK government to develop that antenna, and that's 3, 4, 5 meter diameter. They're large structures, but they deploy using a understanding we gained from this material, and then we launched, and we continue to do our PhD level understanding to get the maths, the understanding of how the chemistry comes together, of how this operates and how strong and rigid it will be in space. But that understanding, building that up, it's bite-sized, it's baby steps, and it's one of the most important things I think the space industry can reaffirm to a lot of other industries, that on these large complex projects, and we'll know these from HS2 and these large projects, they're exactly the same. You've got to break them down into small bite-sized issues, and the more you can empower those teams to deal with different challenges on accuracy of track lines or of whatever the challenge is, that's where your engineers want to be. They want those challenges and finding out solutions. The more you can empower those small teams, the more they can come up with wild, fantastic ideas that when you actually look into it, work out really well. And that's what we try to do here. Be as innovative as we can, be as creative, bring in new ideas like new material sciences. Carbon fibre is not new to most of us, but space is very conservative about adopting this because they want to know exactly how it will work in space. We've turned around and said, well, the best way to find that out is stick it into space. Go and try, find out. So we've got to a point where we can put it into space and see how it works, and then use that to justify all of the analysis that we've done. And we've done a lot of analysis. But hopefully that gives you a little bit of an idea of what we do and why we do it, and why we're so creative and people are interested in what we're doing. At the end of last year, December, we got awarded, we've had a number of awards for our innovation, but one of the awards we got at the end in December was we were ranked 52 out of the top 100 fastest growing companies in the UK, which we're really proud about. But it's more important than that, because space, we've already said, it's 10-year development, it's not fast growing. And of space, the hardware side is the hardest to get into space, because if that fails, you're probably not going to be operating a satellite at the end of it. So we're the slowest part of space, and for us, as the slowest part of a slow industry, to be that fastest growing company in the UK, number 52, That's amazing. That is truly revolutionary, and that shows how we're not only dragging vast parts of the space industry into this new century, we're helping to really invigorate the UK and should hopefully bring some of these ideas to others as well.
It's certainly caught momentum now.
Yeah.
And in terms of, you call it new space, and is there something that we should be aware of, as architects, as any other designer out there who is trying to apply the wisdom from the space industry to kind of other industries on the planet? Is there something that's direct that you...
Yeah, I guess for me, one of the areas I think least about in space, I mean, it's a wide range. There's space art, there's space architecture, there's a whole plethora of different elements of the space industry. But most of what we tend to do, particularly in the UK, is working on satellites, which is where we get information about the health of the Earth, about GPS data, so we know where we are. Telecommunications, we lead the world in telecommunications, and that's fundamental in this day and age, to be connected to not only the person down the road but around the world. Whenever you get the Olympics live from Beijing or wherever else, you're using that satellite infrastructure to provide you that information. So there's an awful lot of business in that, and some real good money and potential for growth in there, and a lot of new space opportunities there. But the area that tends to capture the public interest most is manned space. Now, manned space is the most expensive element, which is why back in the 80s, Maggie Thatcher and those guys, they all decided that they would focus on things like telecoms, and therefore we really had a big bang for our buck and a big return on investment for our buck. So we've really been very commercial in our development. But what we realised recently, with people like Tim Peake coming to the fray, is that manned space is the area that inspires people, and it's manned space that can have some real societal benefits. It's the easiest opportunity to show and to bring to your children, to say, why should I study maths or physics or chemistry? It's boring. It's exciting, it's invigorating. You've got this great universe out there, look at it, you can get your telescope and have a look. And if you do well enough, you can be one of those astronauts that go out and explore. And even from a religious perspective, the amount of early astronauts that got to space and either found religion or reaffirmed their religious beliefs, that unity of humankind. Why are we fighting over that border? There are no borders from space. And how thin the atmosphere is, how we need to look after this planet we're living on. The Gaia Earth, the green movement, it pretty much began or was embellished and grew because of the space industry, and how the astronauts just happened to take a photo of the Earth as they were going around the moon and then coming back. No one in that industry thought that the most used photo that they ever take, that is, I think, the most used photo in the world, is that marble of an Earth in the distance. That's our planet, that's where we live. We probably should look after it. And it's that kind of inspiration and perspective that space is uniquely empowered to bring to us. You could say, going and looking at the Earth's oceans, that's shown us about how we're throwing away all this plastic, how it's a similar kind of aspect. But what space and that manned space opportunity really brings to us is that opportunity to understand how the human body operates in this zero-G environment. It's the best way for us to understand how osteoporosis affects our bones, how you get this bone wastage, this muscle wastage in zero-G, because there's no G forcing your bones to stay strong. And that's a problem that affects a vast majority of women as they get older, and men as well, but it's one of those ones that's very unfair and focuses on the old women and as they're going through menopause. And this is one of the best ways to understand that process and to work out how we can reverse that. Another example that I'm really passionate about myself is that manned space. We're already looking at how we're going to take people so we can not just visit the moon or Mars, but live there. And we're going to have to start being really smart. We're going to create structures that can survive against that harsh radiation environment. So we're going to have to use what they call in situ resource utilization. And that's where we're going to have to work out how do we use that local dirt, that local materials, and make our own mud huts, basically. But yeah, we've done that in the past. We've been very self-sufficient in the past, but we're not now. And we're still very wasteful now. And if you want to understand how we can actually recycle that much more, how we can be that much kinder to our own planet, it's bizarre, but sending people to Mars and giving them that challenge, you're going to have to reuse all of that water. You're going to have to be self-sufficient on a village scale. Well, you're going to get a lot more inspired, intelligent, focused engineers, scientists, people solving that problem, and you can then use those lessons right back home in your house. But you're not going to be able to get those people to work in that at home because they won't be inspired, they won't be driven, they won't be challenged. And that's where the benefit of space is so misunderstood. Why do I want to go and look at another planet? We can't look after this one. It's the other way around. By going and looking at Venus, where you get this massive greenhouse runaway effect for ages, go look at what's happened there. That will give us the cheat book. That will give us what will happen if we don't look after ourselves. It'll be in our face, and it will teach us a lot more than we can learn from this planet alone. So I think it is the most expensive area, and we don't do much of it. But really, we should be doing more, because that's where we're going to have to work out, how do we build these structures? How do we build them so people don't go mad? You know, if you're disconnected from Earth, you're going to feel very alone. How do you manage that psychology? We've really had to do a lot of psychological analysis to understand how to make that space station in space, the ISS, somewhere that can be a home for those astronauts for a year. Jeez, going somewhere else, that's even more of a challenge. And those lessons are what we can use here. What colour should our walls be? How do we make an environment that's more creative or more conducive to harmony? These are things that really can be taken to so many other industries, in architecture particularly. There's a world of challenges for you in the space industry, and a world of lessons for you to learn from what we've already done. And we have done a lot of it, or looked a lot into it, but it won't be known to be correct until we actually get there.